In today's class, I'm on page 61 of the notes, and it's a very, very important material we're going to go down through, and it must be known and memorized. Hopefully, you get through this okay. We talked about the alkanes for the previous part of this week. The alkanes are the first homologous series we study on this course. The second is the alkenes. Now, the alkenes are also hydrocarbons, and are characterized by this carbon-carbon double bond. Each alkene has a carbon-carbon double bond. Now, I said before when I was talking about the alkanes that every carbon atom should be involved in 4 bonds. Well, in an alkene, where the double bond is concerned, each carbon is involved in 2 bonds. You can see them there. There's 4 electrons being shared, 2 in each of the dashed lines if you're with me there. So there's going to be 2 hydrogens bonded to this, and 2 hydrogens bonded to this for the first member of the alkenes. If you remember, 2 carbons gave us ethane when we were talking about the alkanes. So 2 carbons here give us ethene, and the molecular form of ethene is C2H4. It's a colourless gas, and it's a very, very important compound on our course. Now, in the alkenes in our course, we only need to know a few of them, not as many as 8 or 9 as we had with the alkanes. So we only have to know the next 2. You'll notice that here we go. I put in my carbons first when I'm drawing these structures. I put a double bond on the first and second carbon. There's no double bond placed on the second and third carbon. There's only one double bond in each molecule. So it's not double bonds everywhere. There's only one double bond in the entire molecule, and it's on the first. You can place them on the first and second carbon for the moment. We'll talk about that later for other carbons. So here I'm going to have 2 more hydrogens involved here. Now if you look at the center carbon there for the next member, it's already involved in 3 bonds. So there's the 4th hydrogen, and the last carbon there is involved in 1 bond. So there's 2, 3, 4 bonds to complete the molecule. And the name of that molecule is propene, and its molecular formula is C3H6. If you look very, very carefully, C2H4, there's twice as many hydrogens as there is carbons. Same for propene, C3H6. So the next formula is going to be C4H8, you'd imagine, and it is. And let's draw it in. Before we do so, let me just mention 2 very important uses for these compounds. Ethene is commonly used in industry to produce the plastic bags called polythene by a process called polymerization. So the 22 cents you pay in the supermarket for the bag or whatever, there's literally billions and billions and billions of ethene molecules forced together under pressure, because ethene is, of course, under normal circumstances, at normal temperatures and normal pressures, going to be a gas, as we'll see in a moment. Propene is used to produce much harder plastics, like the sort of plastics you'll see on the end of a knife, or as you can see in that gadget there. So you'll see it on kitchen knives and sort of harder plastics associated with them. We have to know another alkene, and it's the one with 4 carbons in it. So I put in my carbons, put a double bond at the first and second carbon, and everywhere else, well, I fill in the hydrogens then. The first carbon's already involved in two bonds, 3, 4, okay? The second carbon, look carefully, is involved in 3 bonds. There's the 4th. The third carbon is involved in 2, 3, and 4. And the last carbon is only involved in 1 bond there, so 2, 3, and 4. And that completes the structure of butene, and its molecular formula is C4H8. So what do we need to know about the alkenes? They're hydrocarbons, so that makes them excellent fuels, just like the alkanes. And they burn in oxygen to produce carbon dioxide and water. So if I take ethene there, C2H4, and I react it with oxygen, O2, well, I'm going to get carbon dioxide and water produced, and I'll also get heat. And the heat can be used for a variety of things. If you look on the left here, I've got 2 carbons in ethene. On the right then, I'm going to place the 2 in front of that carbon dioxide to balance the carbons. On the left, I've got 4 hydrogens in ethene, so I'm going to place the 2 in front of that water to balance the hydrogens. Now look carefully on the right, you'll see 4 and 2 is 6 oxygens. Hope you can see that on the right of the equation. Therefore, I'll place a 3 in front of that O2 to balance the entire equation. Go back and pause the video and rewind for that explanation again if you didn't quite understand it. Ethene, propene and butene are all colourless gases at normal temperatures, so at room temperature. They're insoluble in water and are non-polar compounds. All hydrocarbons are non-polar, and that's the reason why they're insoluble in water, because water is polar. So like dissolves like, so non-polar will not dissolve generally in polar. So consequently, ethene, propene and butene are insoluble in water. And the only main intermolecular forces that therefore exist between ethene, propene and butene, the alkenes, are weak van der Waals forces. What do you think is going to happen to the boiling point as we go from ethene to propene to butene? Will the same thing happen? Will the van der Waals forces get stronger just like they did in the alkanes? Well, they will, okay? Ethene evaporates, turns from a liquid into a gas at minus 103 degrees Celsius. So if you want to take ethene gas and turn it into a liquid, you're going to have to plunge it into an environment where it's minus 103 degrees Celsius, very cold of course. Now propane's boiling point increases to minus 47 degrees Celsius, so that's a dramatic increase of 56 degrees Celsius. It's still quite a cold temperature, but why is there an increase over propene? Because the van der Waals forces are stronger. Why are they stronger? Because there's more atoms. And the second reason, of course, is that when we have more atoms, we also have a higher relative molecular mass. More atoms implies more electrons. More electrons implies stronger van der Waals forces. And the last compound that we're dealing with here, last alkene, is butene. And butene evaporates at minus 6 degrees Celsius. So you can see quite clearly that as we go from ethene to propene to butene, as we go from ethene to propane to butene, the boiling point actually increases. So what do you think the next member of the alkenes will be? The next member of the alkenes is pentene, and it evaporates at 30 degrees Celsius, just above room temperature. So therefore it will be a liquid at room temperature. We don't need to know anything about pentene though on this course. Okay, so I just want to look at the structures again. Look at the structures very carefully. In the double bond, the carbons are classified as planar carbons. So in ethene, I've got 2 planar carbons. I've also got 2 planar carbons in propene and 2 planar carbons in butene, because the double bond in the double bond, the geometry around the carbons is planar. Where, and we mentioned this before, where a carbon is involved in single bonds only, it's classified as a tetrahedral carbon. So there's a tetrahedral carbon in propene and 2 tetrahedral carbons in butene, but in the first member of the alkenes there's no tetrahedral carbon. And as I move on, you'll notice that there's no such compound as methane, because methane implies there's only 1 carbon, and of course you can't form a carbon-carbon double bond if you've only got 1 carbon. Now, a double bond tells us that each of these compounds is classified as an unsaturated compound. The double bond makes them extremely reactive substances. And let's get this definition into our heads. It's a very important definition. An unsaturated compound is a compound containing a carbon-carbon double or triple bond. And what's equally as important is that we need to know 2 laboratory tests to test for the presence of an unsaturated compound on this course. 1, we add bromine water to the reagent in a test tube. Now in our case it's going to be a gas in a test tube, but it could, in other circumstances it could be a liquid. And bromine water is usually yellow and very dilute. It could be red-brown if it's quite concentrated, but it's usually yellow when it's dilute, and a yellow to colourless colour change will prove the presence of a double or triple bond. In other words, it will prove the presence of an unsaturated compound. My second test is to add acidified potassium permanganate to the reagent. We shake the test tube, and a pink to colourless colour change is observed, and this proves unsaturation. And I'm going to show the following video, which I have temporarily borrowed from Foland's. I hope they don't mind. I've given them accreditations at least. There's ethane gas in that test tube, and you can see there's bromine water being placed in there It's very dilute because it's almost very light yellow in colour. And there's gas above that, and the test tube is sealed, and you can see that it doesn't take much shaking to prove that a colourless colour change is observed. And for acidified potassium permanganate, which is pink when quite dilute, a similar test, if it's placed into a test tube of ethene gas, it looks as if there's nothing in the test tube, but the gas is of course colourless. And when the ethene and acidified potassium permanganate are shaken, we get a pink to colourless colour change, which proves unsaturation.